course, we have discussed some of the fundamental ciphers. Till previous class, we discussed, we gave introduction to security fundamentals. Okay, we spoke about what are meant by, the confidentiality, integrity, all these security fundamentals, crypto attacks, the security services, security mechanisms, security objectives, all those things we have discussed, and OSI architecture, the network security model, then types of attacks. Then we have introduced cryptography. Then we talked about crypto fundamentals, right? Crypto fundamentals. Then we introduced, the classical ciphers. Okay, several classical ciphers we have discussed. Before we proceed, today actually we are going to introduce the one of the standard encryption algorithm. Okay, when I say classical ciphers and when I say standard encryption algorithm, what you need to understand is these classical ciphers, whatever we discussed, are not meant for your, the digital communications. Okay. Okay. And the reason is these classical ciphers are having inherent vulnerabilities, and they are very easily, they can be broken with cryptanalysis techniques. Then the people have understood the need for going for the standard encryption algorithms, and especially after 1970s, we have seen various standardized algorithms. When I say standardized algorithms, the algorithms have come both from industry and academia that helped the digital communications to secure things, okay, or secure the communications that are getting exchanged. Okay, before we proceed to the cryptography standard techniques, any cryptographic algorithm, okay, you take any cryptographic algorithm, we have seen that it can be classified based on, the number of keys it is using. We said if it is using single key for encryption purpose and decryption purpose, the same key it is using, it is called symmetric encryption technique. Okay, if it is using two different keys, it is called asymmetric encryption. Okay, so this classification is based on number of keys that are used. Okay, then we have another variety of classification. Okay, so that classification is based upon whether you are performing substitution operation or whether you are performing transposition operation. Right, this also we discussed. So type of operation, whether you are substituting or whether we are transposing. So it is permutation. Is this we discussed or not? Hello? Are these things we have discussed?
Yes, sir. Yes, sir.
Now, yeah, now let us see how another classification on how plain text is processed. Okay. You have the plain text getting processed in two varieties. That is block based and another one is stream based. Okay, so that means cryptographic algorithms based on the number of keys, based on the type of operations, and based on how plain text is getting processed. If you notice, in the way the plain text is getting processed, you take, when you have a plain text, from the plain text, you take the blocks, okay, and you divide the plain text into various blocks and perform the processing. It is called block-based encryption algorithm. Imagine if I am taking each string of the, or not string, each alphabet of the plain text, then what we are doing is you are performing stream-based encryption. Okay, so let us see how actually it happens in both the cases. I will just show you the the diagram. Let me display this. Okay. Is this diagram visible? No, right?
No, sir.
Okay. Okay, now it is visible.
Yes, sir.
Yes, sir.
Okay, 1 minute. Uh, is this visible now? Okay, I think it is visible, right?
Yes, sir.
So now if you notice, this is stream-based. The one what you are seeing on the screen is stream-based encryption, where you are going to take the key bit stream. Similarly, you are going to take plain text bit stream. Okay, so alphabet by alphabet from the plain text, alphabet by alphabet from the key string. Then you are going to combine the plain text with the key. That how you are going to combine, that depends upon the encryption algorithm. Okay, so you combine plain text alphabet with the key alphabet, then you produce ciphertext alphabet. And at the receiver, you are going to perform again decryption bit by bit. When I say bit by bit, it is that you are doing actually alphabet by alphabet. Okay, so you take the ciphertext stream, perform the decryption with the help of your key stream. Okay, so it is stream-based encryption. Now, what happened in the case of block-based encryption is this. Are you able to see the block cipher? So
Yes, sir.
what you do is you take the plain text, okay, which is in the form of a block. Okay, and that block size is b number of bits. Remember, your actual plain text size is n number of bits. Imagine plain text size is total plain text size is n bits. You divide that into different blocks where each block is of b bits. Certainly b is less than n. So you take key block. That means from the key, again you take key also you are going to divide into the blocks, and you take the key blocks and perform the encryption. Okay, but remember, when you are doing the encryption, when I say key blocks, what actually you are doing is, you take key as it is and you submit it to that particular block. Okay, when you do that, there is a trick here. Okay, so means what? I have the key. Okay, and I have say 5 blocks from my plain text. I have created block 1, block 2, block 3, block 4, and block 5. I'm submitting a key to the encryption algorithm. So what happens is, from this key, I am going to generate subkeys called K1, K2, K3, K4, and K5. Okay, these are all called subkeys. And they would be generated from your main key. Okay. And remember, these keys also would be of length b bits. Okay, remember, you have b bit block. So key is also would be of b bits, and you submit each subkey to process each block. That means to generate ciphertext from that particular block. So you have the key, which is the original key. From that you generate the subkeys and provide each subkey to each block of the plain text and generate ciphertext C1, C2, C3, C4 and C5. And at the decryption, again you supply the keys and get your the plain text back. That means B1, B2, B3, B4 and B5. Okay. Are you able to follow what we are discussing?
Yes, sir.
Now, you need to be a little more, make much more attention. When I say here, I think you need to get a little more clarity here. When I say the subkeys, actually what you are going to do here is that probably I'll just erase this. Okay, let me. Okay. Okay. This. Okay. Okay. We will come to the. Okay. Let me write like this. It's only K. Okay. We will come to the subkeys little later. Okay. So what you are going to do is you are going to submit the key to each block. Remember, it is the same key. Okay, whatever the key you are giving. The subkeys concept is little different, that I will be discussing it a little later. So for now, let us focus only on the keys. Okay, so you submit the key and you process the block, you get the ciphertext. You submit that same key, whatever you have given, and you get the second ciphertext of the second block, third ciphertext, fourth ciphertext, fifth ciphertext. Is that clear? When you submit, when you are performing the decryption, again you give the key, you get your plain text blocks. Is this clear? For now, for time being, you just erase you from your mind about the subkeys. We will discuss subkeys little later, but you take it as you are going to give the key and same key here. Is that clear?
Yes, sir.
So once again, I repeat, just forget now for time being the subkeys. You have your plain text, which is divided into different blocks. Okay. In this case, I'm giving you an example where your plain text is divided into 5 blocks and each block is getting processed with the same key, whatever you have submitted, and you are getting the ciphertext C1, C2, C3, C4, C5. Now, when you are doing this, one advantage of doing in this way is, you are performing independent processing of the blocks. That means this particular block is processed with K. This particular block is processed with K. This particular block is processed with K. Do you see any kind of dependency here in the output? What we are getting C1, C2, C3, C4, C5? Is C2 is dependent on anything else other than B2 and K? Is C2?
No, sir.
No, right? C2 is dependent only on your B2, that is the block, plain text block, and the key. Similarly, C3 is based on B3 and K. Correct? So this is a independent processing. So what you can do is, in case if you are following this strategy, this can be optimized by performing the operations in parallel, right? So you can do some kind of a parallel processing so that you can have multiple threads running, performing the encryption of block 1, block 2, block 3, block 4, block 5. And so you run 5 threads and at a single instant of time, you can perform the encryption and generate C1 to C5. Is that clear? Is that clear?
Yes, sir.
Now, in the same block cipher, you have one more principle where I take first block, submit the key and generate the cipher text C1. Now I have second block of plain text. What I'm going to do is, in order to increase the complexity of the encryption, that means to provide more security, I am going to combine this C1 with B2. Okay, I'm going to combine it. So that means my second step, what I'm going to do is B2 is combined with C1 and I'm going to get some intermediate text, right? So called so T2. Now this T2 would be combined with K to produce C2. Is that clear? What I have said? C1 is combined with B2. Okay. When I say combined, what you are doing is you are performing bitwise XOR operation. Hello, are you able to follow what we are discussing? Any doubts?
Yes, sir.
Shall I repeat? So I repeat. You have a plain text that is divided into, in this example, 5 blocks, where each block is of B bits, right? Now, when you encrypt B1 with K, you get C1. What would be the length of C1? What would be the length of C1 or C2, C3, C4, C5? What is the length of C? What is C? Ciphertext of the plain text in the block. What is the size of block?
B bits.
Ciphertext of plain text block. So obviously ciphertext would be B bits, right? So now what I'm doing is, earlier we have just taken each block and performed the encryption C1, and you take B2, apply key, you get C2, take B3, apply key, get C3. This is how we have processed. This is independent and hence you can do parallel processing. What we are discussing now here is, we are taking output of each block. So that means I'm taking for second block, that means B2. Before processing B2, I am combining that with the ciphertext of B1. How I am combining it? I am combining with the typical XOR operation, bitwise XOR. So obviously, when I do this bitwise XOR operation, what would be the size of this output? The T2. What is the size of B2? B bit. What is size of C1? B bit. You performs B bit, B2, B bit, C1 XOR, you get B bit T2. Correct? And I am performing encryption with the help of key. I get C2. Is this clear? Similarly,
Yes, sir.
I take B3 And what I'm going to combine? For processing B3, what I will combine? C2. So take C2 combined with B3. Okay. And apply K, you get C3. C3 would be XORed with B4 and apply K, get C4. C4 would be XORed with B5. So is this process clear? What we have narrated? This is called cipher blockchaining. Okay. So this mode of operating the block ciphers is called cipher blockchaining. Is this clear?
Yes,
Any
sir.
doubts? Any doubts? I pause here for a second, and then if any doubts are there, please ask the questions. Any doubts? Okay, if there are no doubts, we will proceed. So now the point is, if you see here, this is your the stream operation where you are going to take the plain text alphabet by alphabet, and you are going to take the key alphabet by alphabet, perform the encryption, you get the ciphertext. Okay, this is the pictorial representation of your the stream cipher. Okay. Now we discussed several ciphers, right? Can somebody tell me what are the various stream ciphers we discussed? Right from the beginning, we have discussed various classical ciphers, right? Is additive cipher is stream cipher or not? Is additive cipher stream cipher or not?
Yes, sir.
Right. So because what you are performing is typical, you take the key stream, you take your the plain text stream and performing. So typically all monoalphabetic ciphers, whatever we have done, are typical examples of your your stream ciphers. Similarly, Vigneri cipher is also a stream cipher, right? So these are all various stream ciphers we have discussed. So your additive ciphers, monoalphabetic ciphers, Vigneri ciphers, all that. Now, typically, if you notice the block cipher, this is how you are doing the block cipher, right? Are you able to see? This is the block cipher. So what you do, you take the plain text. So this is the block cipher. You take the plain text, divide into blocks. Of course, remember in the slide we have the for the illustration purpose we have taken the block size of 3 alphabets, right? What is the length of the block is 3 alphabets. But in general, you will have 64-bit, then you have 128-bit, 512-bit, and goes with the longer. Okay. So obviously, when you perform the encryption, you get block by block. So this is the cipher block 1. So this is your block 1. This is your block 2. This is block 3. So you have C1, C2, C3. Okay. So in the previous slide, what we discussed was your C1, C2, C3. That means the ciphers that are produced C1, C2, C3. If you notice, either they can be obtained independently or they can be obtained by having interdependency. That means C2 is dependent on C1, C3 is dependent on C2 through kind of block chaining mode. Okay, the cipher block chaining mode. It's called cipher block chaining mode. So is this clear? So when you notice, so far whatever we discussed, your Playfair ciphers, okay, the Hill cipher, these are all typically examples of block-based encryption. Is this clear to all of you? Any doubts? Hello?
No, sir.
So this is, you need to understand very carefully. We discussed stream ciphers. We discussed block cipher. We said your encryption algorithms can be classified block-based encryption algorithms or the stream-based encryption algorithms, right? We said symmetric, asymmetric. Then we said, substitution, transposition. We said now how you are processing your plain text based on that, whether it is stream-based or block-based. So this is what we discussed so far. Okay, but in practical, whatever we discussed the examples, Playfair cipher, Hill cipher are the example of the block cipher. Your additive ciphers, monoalphabetic ciphers, these are all the examples of the stream ciphers. But in practical, the standard ciphers, they have both block and stream. They are both block and stream cipher. Whatever the encryption algorithms we are going to see from now onwards, they are both block and stream. Is that clear? Is that clear here? Shall we proceed further?
Yes, sir.
Now, let us see the importance of this discussion or importance of the stream and block. Now, all of you please read this particular problem. Imagine you have a block cipher where the length of the block, that means size of the block, is 64 bits. And there are 10 1 bits in the ciphertext. Okay, there are 10 1 bits in the ciphertext. Okay, so that means when you see the ciphertext, you have 1 bits in 10 in number. Now the point is how many attempts, that means if attacker is performing a brute force attack, how many attempts need to be done to recover the plain text from the ciphertext? Okay, so you have a plain text of length 64 bits. You have a plain text of length 64 bits. When you took the ciphertext, you have seen there are 10 ones in that. Okay, imagine if the cipher is designed as a substitution cipher and Imagine if the cipher is designed as a transposition cipher. Can somebody tell me what could be the answer? Imagine if it is a block cipher, substitution cipher, what happens? And if it is a transposition cipher, what happens? Oh, what happens in the case of A? What is the length of plain text?
64. Yeah.
So you have length of the plain text is 64 bits. So obviously, when you perform substitution, what you are going to get is 2 power 64 bit possible combinations, right? Right. So an attacker, he has no idea, especially about which bit is substituted with what bit. That's what is actually the goal of substitution, right? What is the goal of substitution? To create confusion. The goal of substitution is to create the confusion. So the attacker do not have any idea about which bits are substituted with what bit. Okay. So because of that, what happened is, okay, just I'll give you the answer. Let me. Are you able to see the answer? No? So in the first case, that means where you are performing the substitution, Eve do not know how many ones or zeros are there in the plain text. Okay, so whether he do not know the cipher text was produced from a 1 or 0. Okay, so he has to try all possible combinations of the bits. Whereas in the case of the second scenario, which is transposition, what is typically transposition? You are permuting the bits of the text, right? So as we discussed, you take VAT, what you are going to do is I'm going to just permute the positions of the bits like TIV. Right? So when you know that there are 10 ones in the cipher text, that means there are 10 ones in the
Plain text.
That's all. So the point is your search space gets reduced in the transposition ciphers than the substitution ciphers. Okay. So we need to understand the importance of each of these the operations like substitution operation and a transposition operation. Then the way you are processing your plain text, block based or stream based. Similarly, you are talking about the number of keys. Okay, key whether it is symmetric key or asymmetric key. Now, so these are all things which you need to remember before we proceed further to the next standard algorithm called Data Encryption Standard, DES. Okay. So this is the Data Encryption Standard is one of the the early designed and more standard encryption algorithm. As I have already said, when I say standard, because it was first commercially It is the first commercially deployed. Are you able to see the text? Okay, so the DES is first commercially deployed encryption algorithm. And remember, it is performing both operations, substitution operation and transposition operation. And now the point is, when it is performing the encryption process on a particular block, it is going to perform that encryption operation not one time, but a total of 16 cycles. This is very, very important. So that means what the algorithm is doing, algorithm takes a block, say B1, and apply the encryption algorithm over the block with the help of key, then you get a ciphertext, right? So it's not that you stop with that. Again, you apply the key, get another ciphertext. Again, you apply the key, you get another ciphertext. So proceed like this for about total of 16 cycles of operations. So 16 cycles of what operations? Both your substitution and transposition. That makes this particular algorithm, that made this particular algorithm more robust and first commercially deployed algorithm. Okay. Are you able to follow?
Yes, sir.
Yeah. So now let us see how it is doing it. So all of you are able to see the image.
No, sir.
1 minute. Okay, now this is how your algorithm is going to work in each round. We said 16 rounds of operations, right? So the DES is performing 16 rounds of operations on the data block. That's what we said. So what it is going to do is it takes the data block and divides that block into two halves called left half and right half. Then keep the left half of the text as it is, but do some operations on the right half. Okay. What operations? Take the right half of the block, combine that with the key, whatever that is given, the key. When I say combine, it is typical XOR operation. So whatever the resultant output, you are going to perform some substitution. What substitution? We will be discussing it little later. Output of that would undergo some transposition. Okay, that's what is written as permute. Then whatever the output of this, that would be combined with the left half. When I say combined, the left half would be combined with this output. So perform XOR operation. So whatever the output of this would form the new right, and the previous right is the new left. With this, one round of operation is completed on the plain text block. Now you take these two halves, left half and right half, keep left half as it is, perform these operations. Is this clear? Any doubts? Any doubts?
No, sir.
Now the point is, you have given the key here, okay, for first round. So there is a key. From that key, you are going to give one key. This is called actually sub key. Okay. I hope you guys remember a few minutes back I used the word called sub key. Okay, that is where the sub key comes. From the original key, whatever we have given, we are going to generate a sub key and give it to the each round. So this is the sub key for first round, and then you submit sub key for second round. That means for every round you are generating a new sub key. Okay, like this, how many new sub keys would be generated? How many new sub keys would be generated?
16.
So totally you are going to get 16 sub keys that are generated from the original key. Okay, so that is the reason why when you look at the DES, or maybe in the next classes we'll be talking about the AES. If you see, you will have encryption algorithm, you will have decryption algorithm. Of course, we will not discuss decryption algorithm much. The reason is it is exactly the reverse process of the encryption algorithm, but there would be a algorithm called key generation, sub-key generation algorithm. So these are the important things in the DES. So your encryption algorithm and key generation algorithm. Because in the encryption algorithm, each block is getting processed in this particular manner. And each key, whatever you submit, of course, remember, imagine you have say 5 blocks. You are going to submit the original key to all 5 blocks. But when the block is getting processed, you are going to generate the new subkeys. Okay. So I repeat again, you are having a original plain text and original key. Original plain text is divided into, see, plain text P and key. Plain text is divided into blocks B1, B2, say 3 blocks, B3. Now the key is same. Key is same for each block, but when it is processing B1, it generates 16 subkeys. Similarly, same key is given to B2, it generates 16 subkeys. Same key is given to B3, it generates 16 subkeys. Is this clear? Hello?
Yes, sir.
Yeah.
Yes, sir.
Yeah. So now let us see how actually this is proceeding. Now let us see the play. Okay. Moment. I think this copying text is creating a problem. Okay. So now let us see how the encryption algorithm is working. Okay. So the data encryption standard algorithm is going to take 64-bit length block. Okay. So the block size is 64-bit. So that means imagine you have a plain text P that is divided into blocks, block 1, block 2, and block 3. Each block is of 64-bit. So take 64-bit, process it. Take 64-bit, process it, and take 64-bit, process it. So this is the input to the algorithm. Now, tell me, if I have the plain text of 64-bit, what should be my key size? What should be of key size? See, we discussed the need for having the the relation between the size of the key and size of the plain text. When we talked about this in the Vignari cipher, and of course, yeah. So what should be the key size of key size and plain text size? They should be same, equal, or more or less. What? key size and plain text size. What we discussed. So they are supposed to be the same. Your block size should be equal to the key size. In the other way, key size should be equal to the block size. So is that clear? I hope you guys remember this concept. You remember the binary cipher, we have taken a keyword called deceptive and we repeated that keyword till the length of the plain text. Do you remember that?
Yeah, yes, sir.
Then is the length of plain text and length of key are same or not? Hello, yeah, tell me, yeah.
No, sir.
No. No. You remember binary cipher? We took the keyword called deceptive and we repeated the keyword so that your length of plain text and the length of key are equal. Do you remember that?
Yes, sir. There it's equal, sir. Here
That's
I'm
all.
saying it's not given equal.
No. Forget about here. I have not come to the point. So
Okay,
typically your plain text and key should be of equal length. So what should be the key size when I have the block size of 64-bit? Key size should be
64 bits.
So typically the DES algorithm has key size of 64-bit. So when you are performing encryption, you have to submit 64-bit length key. You have to submit 64-bit length key. But what the algorithm is going to do is from the 64-bit length key you have given, algorithm is going to consider only the 56 bits. So 8 bits are truncated. The reason or for what purpose they are truncated and later how they would be used, we will discuss it little later. But these 8 bits are truncated and hence your key size of 56 bit. Okay. So you have the plain text block 64-bit, key size 56-bit. They would undergo the processing of what we have discussed in the previous scenario. Okay, like this. And once you complete 16 rounds of operation, after 16 rounds, you get the cipher text. What would be the length of cipher text? Obviously, what is the length of plain text is your length of cipher text. Okay, so this is your input to the DES algorithm and this is the output from the DES algorithm. But how this is going to happen, how the algorithm is going to perform. So the plain text is undergoing initially a process called initial permutation. Now tell me, when I say initial permutation or when I say permutation, is it the substitution operation or is it a transposition operation?
Transposition.
So it is typically a transposition operation that is done on the plain text so that what you are doing is you are rearranging the bits. OK, so that means what? You have 64 bits, you arrange the bits. So say take an example, 40th bit you keep it in the first location, then 30th bit you take it and then keep it in some other location. So you are going to just perform the permutations. So whatever the permuted input or the text that has undergone the permutation, it would undergo 16 rounds of operation. That means in the previous slide what we discussed, this particular operations, before that you have some permutation operation that is done. Okay, so the output of that permuted text would undergo the 16 cycles of operations. That's what it means. Okay, since it is 64-bit, when you divide it into two halves, you have left half of 32-bit, right half of 32-bit. And you keep the left half as it is, perform certain operations on the right half. That's what we have seen here, right? Once you complete the 16 rounds of operations on this block, then whatever you get at the end of the 16th round, you call it as a pre-output. That particular pre-output would be again undergoing the inverse permutation operation. Remember, you have already done the permutation here. For that, this inverse operation would be done here. That means, imagine here when you change it the 40th bit location to the first bit location, the inverse process of it. Whatever the first bit that is there in the pre-output would go to the 40th bit location. Okay. So that is the ciphertext. Is that clear? Hello?
Sir, can you go back to the last slide 1 second?
Yes. If you have any doubts, please ask. If you have any doubts, please ask.
Sir, can you explain this inverse permutation once?
Yeah. So what we have done in the first step is the permutation, right? What we have done in the first step is the permutation. Means what? We just altered the positions of the bits. We rearranged the bits. So one typical example is that first bit has gone to the 40th bit location. First bit has gone to the 40th bit location. And we have done this processing. Now at the final stage, after performing your 16 rounds of operations, whatever the text you get, that would undergo the inverse process of your first step. What is the inverse process? You take your 40th bit, what is there in the ciphertext, that you bring it to the first bit location. That's what is your inverse permutation.
Okay, sir. It's just inverse of the first step.
Correct. It is just inverse of the first. We will discuss this with an example, when we are proceeding further. Now, yeah. In the previous slide, we also discussed about the key. Okay. We also discussed about the key, and we also discussed in the further key before slide, we also discussed about from the original key, you are generating the subkeys. And we said that, remember, you have a key generation algorithm. So what is that? If you look at the key generation or key processing, what is the initial key you have given? 64 bit. I said your 64 bit is going to get truncated to 8 bits are getting truncated, and you get a 56 bit length key. So once you get that 56 bit length key, that will undergo some kind of a permutation. Again, this is transposition, right? Once that is done, for each round of 16 rounds, we have to generate a new subkey. Okay, a new subkey. You have to do some operations. What are the operations are like, left circular shift, some operations that we will be discussing it in the upcoming minutes. Okay. Once that is done, for every round, you are going to generate a new subkey. So that means typically if you look at, so initially you have given 64 bit. Okay. From the 64 bit, for every round, you have to generate 64 bit into 16 rounds. Okay. So these many keys you are going to generate from the original 64 bit key. Okay. So this is how your key gets processed. Remember, we are going to discuss it at length with an example. Okay. So this is the overall process. Is this clear? The process, not how it is done, but process. Okay. Now let us go to the next concept. So this is the overall encryption overview. Okay. All of you are able to see. We are going to take the 64-bit plain text block. Remember, you may be having several blocks like this. Okay, block 1, block 2, block 3, block 4, like this. You may be having several blocks. So for each block, what we are going to do is you take the block and initially perform transposition. Okay. Then when you perform transposition, the output of that would be certainly 64-bit because you are giving input of 64-bit. Now it undergoes round 1 operation. We have seen what happens in the round 1, right? Then output of that would be 64-bit. So round 2, so on, round 16. Okay. On the key side, what we have given is the 64-bit key. Okay. Then we are performing some permutation operation, which is the transposition. And after that, we are going to pick 56 bits and make it, that means, truncate 8 bits, keep it 56 bits. So length of the key is becoming 56 now. After that, perform a circular shift operation towards the left on the 56 bits. Okay, obviously that would be a 56-bit only, right? Then now again you perform some transposition. Okay. When you perform transposition on the 56-bit length, obviously the output would be 56. But remember, after doing that 56-bit transposition, we are going to truncate something and make it of the length 48-bit. Okay. And that is given as an input to the round. Now in the round, if you take 64-bit, are you processing entire 64-bit? Are you processing entire 64-bit in each round? What you are doing in the each round? We divided that 64 into 2 halves, 32 and 32, right? This is left, this is right. Is it not? Do you remember that?
Yes, sir.
So when you divide the 2 halves of 64 as 32 and 32 and keep left as it is and take the right and process with the key. But what is the length of the right side half? It is 32-bit, right? What is the length of key? It's 48-bit, right? Is there a mismatch?
Yes, sir.
So your length of right half is not equal to the length of the key, or length of the key is not equal to the plain text. But it gets processed. We will discuss that also. Okay. So like this, we proceed further, and similarly, this is a sub key. Okay. Generation. This is the sub key generation here for the round. So goes on for sub key for the round. So you generate, and then finally at the end of 16th round, the right half goes as left and the left half goes as the right as the 32-bit swap. Once that is done, that particular 64-bit would undergo inverse initial permutation. That means for this particular process, inverse of it. This is the 64-bit ciphertext of this particular block. Okay, this is the overall process of the encryption algorithm. Is this clear? Please look at it, and if you have any doubts, ask me. Hello? Is that clear here? Any doubts here?
No, sir.
No doubt,
Now we will go each algorithm by algorithm, each step of the algorithm and proceed. In the plain text, we said your 64 bits of plain text is getting processed. Okay, this is plain, PLAIN, plain. So this plain text is passing through initial permutation, that is getting the bits rearranged. So how this initial permutation is happening, or how you are going to perform the the permutation. If you notice, this is how it happens. There is a table called IP table, called initial permutation table, which says, okay, this is the 50th bit that has come to the first bit as a first bit. 50th bit has come as a second bit. 42nd bit has come as the third bit, and so on. So that means your first bit has gone to this particular location, which is actually the 40th location. Okay. Remember, this is fixed. Is this clear? Hello?
Yes, sir.
This is a typical permutation operation that is done on the text. Okay, so that means when you do this operation, when you take your bits, when you observe the bits, how they are actually done. So this is like this. So imagine this is your plain text bits, original plain text bits. And these are all permuted bits. Okay, you notice M1 has gone here. This is the 40th location. So your M58, okay, somewhere here has come here, the first location. Okay, so this is how your transposition happens over the plain text. Is this clear? Hello?
Yes, sir.
So there is no much complexity involved in this. It is fairly a simple operation of permutation. Next one is, now this permuted text is undergoing 16 rounds of operation, which includes your permutation and substitution. Okay, now you view each of this round as a mathematical function, kind of a thing. Okay, so what is the input to the round is your permuted text. From the original text you permuted, and that is the input. Now you take that permuted text, then you divide it into two halves as 32-bit and 32-bit, one as the left, another one as the right. Keep the left half as it is and proceed with the right half. Now the overall processing of that round can be summarized as like this. Remember, if it is not the first round, the current left would be the previous right, correct? So except the first round, if you notice, once you complete the first round, what is happening? Previous right is forming the new left, right? So the current right, that means the new right, what happened is the previous left combined with the XOR operation by performing some operations over the 32-bit of the previous half with the key. Okay, this includes your some operations such as substitution and some operations such as transposition. Okay, so this is how actually that is represented in the form of a simple mathematical representation. Now, what is this mathematical representation and how it is done? Okay, let us take with an scenario and or let us take and proceed further and explain. So we have this 32-bit of left half. So what you have done, plain text of 64-bit is divided into, first it is undergone the permutation 64-bit, and that is divided into two halves. 32 and 32. And the right 32 only is the one which we are going to proceed. And this is on the key side, right? So your 64-bit of key has undergone some permutation. Of course, we will be discussing that permutation also. And from that, you are going to get 56-bit. And these 56 bits are going to be as a sub key. And then, you are going to create, the sub keys for every row. So this is a separate part. Now you divide this entire process into 6 steps. Step 1, step 2, step 3, 4, 5, and 6. 6 is the key processing. So up to on the plain text side, permutation dividing into 2 halves. Is that clear?
Yes, sir.
Now we are going to process the divided text. We are going to keep the left half as it is and take the 32-bit of right half. Now this right half of 32-bit has to be combined with the key. And remember, a few minutes back we said the key size is of 48-bit. But your plain text, your text block is here, right side is 32-bit. Since this is the 32-bit and the key is 48-bit, this 32-bit has to be expanded so that you get 48. So how the expansion happens? There is a step called, there is a table called expansion table. With that, we are going to expand the 32-bit to 48-bit. And hence, your 32-bit becomes 48 and you can perform bitwise XOR with the key. Since you perform bitwise XOR with key, you are going to get output of 48-bit. Remember, earlier you have 32 and it got expanded to 48. Now I need to bring it back to 32-bit. How do I do it? I do it with the help of a box called substitution box. And once you do that, your 48-bit is going to become 32-bit. Now this 32-bit will be undergoing permutation operation and fetching you 32-bit. So here 32-bit and the left half of 32-bit would undergo a typical bitwise XOR. Okay, and fetching you the new right. And the new left is the old right. Okay, that's what is the function what we have seen. And in that, if you notice, this is about the left one. In the right one, if you see the expansion, the substitution and permutation and combining with the key is represented as a function called f. Okay. Now the point is we have to understand how my 32-bit is becoming 48-bit and subsequently what I am going to combine with an bitwise XOR and how I am making my 48-bit to 32-bit. That and all we will see now. Now do you notice a combination of substitution and transposition operations here?
Yes, sir.
So with substitution, what you are operations you are achieving, both goals you are able to achieve. Okay, is this diagram clear? Shall we proceed? So please keep this diagram in your mind. We will proceed and see 1, 2, 3, 4, 5, 6. So initially, the first step is expanding this 32-bit to 48-bit. How do I do it? It is with the help of a table called expansion table, which is a fixed expansion table as per the algorithm. So these are all my initial the 32 bits that are there, 1 to 32. And I need to make it 48. OK, so I'm adding some 8 bits extra on the left and 8 bits extra on the right. Okay. The bits I am going to add are also fixed. So 32, 4, 8, 12. Similarly on the other side 5, 9, 13 kind of a thing. So now my 32-bit write has become 48-bit. Is this clear? Any doubts? Hello?
No, sir.
What is the next process? What is the next process? What is the second step? What is the second step? We have seen first step. Have you seen first step or not now? What is the second step?
XOR combination.
So we have seen the first step. This is your first step, making expansion to 48-bit. Now the second step is expanding expanded 48-bit to be XORed with the key, which is the bitwise XOR operation. Okay, so when you perform this second step, what you are doing is a bitwise XOR operation with the expanded 48-bit with the 48-bit key. This is a fairly simple step, right? Is there any complexity in this step? Is there any complexity in this step? Hello? Here, is there any complexity in this step?
No, sir.
It's fairly simple, right? This is second step. What is third step? What is step 3?
Substitution.
Okay, substitution for what?
For the expanded bits, we have to reduce it again.
So you are going to make 48-bit to 32-bit. This is somewhat tricky here. Okay, so let us see here. So this is the third step. The result of your second step, where you are combined the expanded 32-bit of 48-bit with the key that is combined with an XOR operation, you have to bring back to 32-bit. How we are going to do is we are going to performing a kind of a substitution. How do I do it? Okay, this you have to listen very carefully. The substitution happens with the help of 8 substitution boxes. Okay, so 8 boxes where each box is taking 6 bits as input. Okay, so 8 into 6, 48 bits as input. They are going to 8 substitution boxes where each box is taking 6 bits as input and producing 4 bits as output. Since it is producing, since the S boxes are producing 4 bits, so totally 8 boxes, 8 into 4, 32-bit. Is this clear? The input and output. So 8 into 6, 8 into 4. Input, output. Number of boxes, number of bits. So pictorially, this is your right half of 48. This is key of 48. They are combined, which is now 48. Now there are 8 boxes, S1 to S8. Each is taking 6 bits as input, producing 4 bits. right? So this becomes 32. Now, how do they produce? How do they produce? Remember, the strength of DES actually lies with these S boxes. Okay. The strength of DES lies with the S boxes. In fact, the design of S box itself is, is a little complex, and let us see how actually these boxes operate. We'll discuss that. Let me give you a moment. Just going to keep things on. What happened is this: my the ActiveInspire software is not working properly, so I have to use the PPT as the notepad. Okay. So now let us see, this is the process. These are all the S boxes. Okay. So you have 8 substitution boxes, box 1 to box 8. Okay. And remember, these designs are fixed, and how they got fixed is after a thorough research. Okay. So design is fixed. You can't change it. You cannot change it. And since the design is fixed and the open design, not only the encryptor but also the attacker also knows the entire structure, right? So each box takes 6-bit as input, produces 4-bit as an output. Now when it is taking each box, say take an example, one box is taking 6 bits as input, so bit 1, bit 2, bit 3, bit 4, 5 and 6. When it is taking the 6 bits, what happens is you see that each box is having certain rows and certain columns. Now the row is decided by your last 2 digits. So B1, B6 decide which row, B2 to B5 decide which column. Okay. And go to the particular block or the element and pick the element. Let us see with an example. Imagine you have an input 011001 for the box S1. What is S1 box? In the previous slide we discussed, or we have shown, this is the S1 box. Okay. If you have noticed in the previous this is your S1 box. Okay. So this is the S1 box. Now 6-bit input is coming to the S1 box. Now these 2 last bits forms the row. So that means this is 00, 01, 10 and 11. So you go to this particular row and 1100 go to that particular column. So that means you go to this particular column and the corresponding number, okay, is your output, 9. So 9 digital value, the binary value is 1001. So your 6-bit has become 4-bit, right? This is from one box. In the similar manner, we do the operation so that you are going to get from 8 S boxes, you are going to get 4-bit output. So that makes your 32-bit. Is this clear? Any doubts? Hello? Hello, yeah, is this clear or any doubts?
Clear, sir.
Yes, sir. Clear, sir.
Remember, you need to understand. Yeah, I'm happy that you are able to follow it. At the same time, those who are really interested, you need to see how these S boxes are designed, and what is the rationality, why these numbers have come, on what basis. Okay, this is all about, in fact, you can see in one of the MOOC course, there is a MOOC course exclusively on how to design an S box. Okay, substitution box. Okay, so there is an exclusive MOOC course. I forgot the exact title of the course. Designing of Boolean functions. Okay, so if you notice, the entire course of 6 weeks is about how these test boxes in the encryption algorithms have come. Okay, so these are all just not like, randomly chosen values. The design of S box is based on certain criteria. Okay, and this particular criteria, how it is implemented mathematically so that, these numbers have come. And remember, most important thing is, I can perform encryption. I should be able to get back, right? So when I am performing the decryption, I should be able to get back my plain text. And these numbers have chosen in such a way that, your entire process is reversible. Okay, number one. Number two, makes this complex so that attacker will not be able to just easily break the algorithm and get the key. At the same time, you keep algorithm implementable, right? Imagine, when this algorithm was introduced in 1970s, it was actually implemented in a practical application, commercial applications in 1977 onwards, and it was there till 1990, early 90s, right? 92, 93 kind of a thing. And in practice, later on, people were able to break this algorithm. But the point is that in those days, your computational power is very minimal. So you need to design an algorithm that manage with the available computational power, but at the same time robust enough to withstand the attacks. Okay, so there is a lot of beauty. Those who are really interested can actually look at the way the way these substitution boxes or permutation boxes, they are designed, the design criteria, and the mathematical steps that are involved. So now the point is that we have understood the algorithm, how it is working. Now, once that is done, we have completed the substitution operation. Next, we have to do permutation operation, right? Is that clear? That is the next step, right? You remember the 6 steps, or you forgot? So the next step would be permutation. So you got the 32-bit output that would undergo the permutation operation. Obviously, you have a permutation table called P table. Okay, and says that, okay, you permute your 32 bits in this particular manner. Obviously, the output would be 32-bit, right? It's a simple process, right? Is there any complexity here involved? Do you see any complexity? Oh,
No, sir.
it's a fairly simple, right? So straightforward. So if you look at overall, this is what we discussed. So you were on the plain text side, on the plain text processing, we took 64-bit, permuted. Permuted is divided into 2 halves, and 2 halves, pick the right half, expanded to 48, and expanded 48 is combined with key. Okay, then substitution operation through 8 S boxes, then permutation operation through P table, and whatever that you get, you have to undergo typical bitwise XOR operation with the left. Okay, so this is about the plain text side processing. Is this clear? I hope you guys recall the initial steps what we have done. Correct? On the plain text side, it is clear.
Yes, sir.
Now with this, what actually we have done is we have actually done only one round. Like this, you have to perform 16 rounds of operations. Okay. Like this, we have to perform 16 rounds of operation. This is on the plain text side. Now, what is happening on the key side? That is another interesting thing. What is happening on the key side is you are taking initial 64-bit key. Remember, I hope you guys remember that, right? So what we do on the key side is this. Initial key length is 64-bit key. Okay. But that actually getting as 56-bit key. How it is done? It is done just by omitting every 8th bit, okay, in the key. So you see 8th, 16, 24, 32, 40, 48, 56, 64. So totally 8 bits are omitted, or you can say truncated. Now the remaining bits will form the 56-bit key. Okay. And what you are going to do with the 8 bits, we will discuss it little later. Now this 56 bits would undergo permutation with the help of a table called PC1 table. What is that PC1 table? That is given here. So that is actually permuting the bits of the key, which is 56 bit key, is undergoing permutation. Okay, is this clear? Step? Any doubts here? Any doubts? Now, whatever that 56-bit key, from that we have to generate what we have to generate. What we have to generate? Can somebody tell me what we have to generate? Subkeys, right? How many subkeys we need to generate? Hello? How many subkeys we need to generate? Am I audible here? Hello, am I audible?
Yes,
Yes,
sir.
sir.
Yeah, how many subkeys we need to generate? 16 subkeys, right? I think you are getting bored. Shall we continue or stop? Hello? Shall we continue or stop?
Sir, how much is left in this part?
We need to discuss the key generation algorithm. That would take another 10 minutes or 15 minutes. What do you feel? You want me to stop? No, tell me,
Sir.
feel free.
Sir, we
Shall
could wait for 5 minutes maybe and then continue.
Okay. You want to break for 5 minutes? Okay. Or you want a break, or you want me to stop? I will stop and then we will discuss it in the next class. That's okay for me.
Yes, I can explain this in next class.
Yeah. So in such case, we are going to discuss the remaining part in the next class. So what we are going to do in the next class is about discuss these aspects. Okay. Go back to this particular this one. Yeah. So we are going to discuss these aspects. Okay. So remember, we have completed this part. This part we have done, the whole part, and this part is remaining. Okay, to generate the subkeys. Okay. So in the next class, we would be talking about the key generation. Okay. And remember, with doing all this, there are certain potential vulnerabilities in the DES algorithm, and with which people have has attacked the DES algorithm. So what are the vulnerabilities or weakness in this DES? Then people have done double DES. Okay, so means performing the DES encryption 2 times. Then triple DES, and remember triple DES is still in place. Okay, so though after introduction of AES, still triple DES is being followed in some of the applications, but very few. Okay, so these things we will discuss in the next class. But for that, what I want you guys is to go back and open your textbook and read what we discussed. Okay, so this is what I want you to do. I hope that you guys appreciate the the